Does anybody have any question about notes that I posted? I think I posted lecture 5 too. So homework, if anything is not clear, you can ask right now. Other than that, we will start the class. Okay, sounds good. Okay. So last class, actually, we talked about like induction. So let's go back and finish what you started. We talked about induction. We talked how does induction work. So let's go and have another example, actually. I will write the example. You guys can think about it. So, and then you will wait like 2 or 3 minutes to just start. So I want to solve this question. I think, did I solve this one? I think I wrote it yesterday. And I asked you guys to think about it yesterday too. So, okay, let x is in R. X is not equal to 1. And then you want to show this. What do you want to show for n greater than 0? Divide by x minus 1. And then we consider this one to be Pn. Just think about it for a minute. So, and then the start. You guys can hear me, am I right?
Yes, we can hear you.
Okay, great. So let's move ahead and then, okay. Anybody has any idea so how we should prove this one? I talked about this one yesterday too, so. What is the step? Yes, we need to do induction because you need to prove and show something. As I mentioned, I just add Pn here. What is the first step?
Get our base case.
Yes, first use this. Okay. Yeah. P0. What is P0 says? As I mentioned, here is n greater than equal to 0. So we start with the base case of 0. So P0 says that this is gonna be k from 0. And then it's gonna be xk x1.
والله وردات سكر حطيتهم في اورنج النهايات مسكحه.
And then what we are gonna say, so this is gonna be x0. So this is gonna be 1 equal to 1. So it's correct. So we show that this is hold. Then what we need to do? What is the second step? If you show the base case is hold, what do you do next?
P1.
Why P1? We don't have P1, so we assume that Pn is true, and then show Pn plus 1 is true, or assume Pn minus 1 is true, and show that Pn is true. That's one of the way. So let's do this one. Show. We just suppose for any n greater than 0, because we show 0 here, you don't need to show 0 here anymore. We say Pn minus 1, gonna show that Pn is true. We assume the first one and show the other one. So what do you say? We say let n greater than 0 be arbitrary any number, but we assume p n minus 1 is true. What does that mean? If p minus 1 is true, this is pn, it means n should be equal to n minus 1. So here we say k from 0 to n minus 1 xk is equal to x. We have here n plus 1. So we put n minus 1. This is become n and minus 1 and this one too. Now we assume this one. Let's show that the other, then what we should do? If we assume, we should show that this is gonna hold. This is true, so it should hold for n plus 1. For n, and this is n minus 1, this is n. So we put this one. We need to show this is true. How do you show that? We start with this one. I know this is true. So let's see. I want to prove this one. So it's like, okay, if I know this is gonna be n xk, how can I show that? I can write like this. k0 to n minus 1 xk and xn here. Just put this one out. Let's see. Okay, so then this is gonna be equal. I assume this is true. If this is true, it's gonna be this one. It's gonna be xn minus 1 divided by xn, and then xn here. So this is gonna be considered by the induction hypothesis. One more thing, whenever you prove this one in your homework or your final exam, you need to write this thing. You need to write by induction hypothesis. You need to mention this one, how you got that equation. It doesn't mean that you need to write it only. Just need to explain. So this is gonna be x minus. Gonna be this one. And let's consider this one x is gonna be this, and then you just multiply this one, it's gonna be x and x and minus 1. What's going to happen? So this is gonna be x n plus 1 minus xn. This can cancel each other, and then we are gonna get to xn plus 1 minus 1 x. So we prove the result follows by induction. So we proved it already. So that's done. Does it make sense? Okay. Okay. That was one of the questions. Let's do another one, actually. Let's do another example. Let's do another example. What is that? Let's see. Say define T of n for all integer number, positive integer number by this definition. We say T of n is if n is equal to 1, it's gonna be 0. If n is greater than 2, this is gonna be T. We need this proof because we use it later. So if n is greater than 2, T of failure of n over 2 plus 1. We say, I know this is a T of n. What do you want to show? Prove for any n greater than 1, t of n is less than logarithmic of n. So that's the question. So this is going to be considered p of n. Anybody have any idea? And then you see this is going to be this one, and then the question is, so okay, if that's the case, and then hence, so it is going to say t of n, it means it's O of log n. That's easy because, you know, if t of n is less than log n, and we know t is positive, so this is going to be O log n. So it's easy to show. We just need to show p of n is true. How do you prove this one, actually? If you want to write a proof, so how do you work on this? Any idea? So this was the question. This is t of n. You want to show this one? Yeah, you need to show all the steps in the homework or quiz, one by one. So what do you think about this question? This is like, when we say proof of this concept, and you have something like some equation or just inequality that shows there is n there for any n greater or less than, so you need to use induction. But how do you prove this one right now? So what is the steps? We explained in the previous page. How do you take the steps?
Is like the base case already proved? Because
Yeah, but the thing
n
is
equals
that
0?
you could not say, oh, we don't need to write it. Although, yes, it's easy, it's just obvious, but you need to show these things. If you don't write it, you're going to lose point in homework, final, or midterm. So you say first step is like showing that P, actually here is, we have P1. It's not P0 because this is a start from 1. We said P1 is the base case. What does it says? It says that T1 is less than equal to log of 1. So what does that shows? T1, we come here, T1 is equal to 0, and log of 1 is 0. We show this is true, so, okay. It holds. I need to make sure that base case holds. So I say, okay, base case holds. Let's do the second part. What is the second part? Second part says, for all n greater than 1, we show that equal 1 is already worked. We said, let's consider P1 all up to Pn minus 1 is true. And then prove P of n is true. So this is going to be like by induction. So how do we work on this? So, okay, I know that I do have all of this. I know this is shows that all of them is, actually this should be 3.1. So this is true. Let's consider a second. Let n greater than 1 be arbitrary. It can consider any. So assume, what do you assume? Assume for all k in the range of k is between 1 and n, that tk is less than equal to log of k. So what does that mean? We consider all p1 to pn minus 1. It means any number between them. What does that mean? Why I write it like this? Because when I say this one, it means pk from 1 to n minus 1 is true. It means all of them is true. So I say, okay, consider this one is true. What should I show? I say, if this is the case, I'm going to show, we must show Tn is less than equal to log n, or log, doesn't matter. So that's what we need to show. Okay, let's consider how it works. So we need to show this one. Say, okay, let's go to definition of Tn. What was the definition of Tn here? I do have a definition of Tn for any n greater than 2. So that's here. We go here, we just, okay, T of n is equal to this number. So let's put it there. This gets T of plus 1. And what can I say? If I say, I explain that for any k greater than 1 to n for this equation, so if the maximum k is this value, n, you do have this one. So here, I do have this. What does that mean? So it means that consider this part to be k. Tk less than L, lower log of k. So it means this is going to be k. Tk, so let's consider this one actually be k. So it means Tk less than log of k. So this is gonna be, actually, let's go back to the color that I used. So this is gonna be log of n over 2 plus 1. So how do I say that? I need to write it again. I will write here. I use this one by the induction hypothesis with what? We consider k equal to n over 2. So let's see, we consider this one holds. Okay, let's see what we can do here. So now I do have this one, but the other things I know log of this, because this is the floor, is less than log of the whole number without the floor. So this is gonna be this value. I do have this point. I know that log of this one is less than log of x. This is one of the things I know already. So this is gonna be hold. So if this is hold, what I'm gonna do, so I go back, I say, okay, this is gonna be hold, and this is plus 1 here. So this was gonna be, I will put this one log. I use the log definition, log n minus log 2 plus 1. Because this is the base is 2, this is gonna be 1. So this is gonna be removed by this one. So this is gonna be less than log n. This holds. So this is one of the most important things you need to know here. So just let me write it here again as a point. So since we say this one, some of these things you need to know in the future. We use this one, and this is log of floor of x is less than log of x. So this is gonna be hold. I use this one here. So I reach to the point. So what I'm gonna say, I will write that then T of n is less than log of n, result so by induction. Already prove it by induction. That's gonna hold. Does it make sense?
Yes.
Okay. So this is some of the things you need to know. Okay. So now we know multiple base cases. We try. So we do some of this actually. So we have different inductions. So we say, okay, base cases can be P of 1, 2, P of n, any base cases. And then we will show that after that it's gonna hold. So, but that's the first thing you need to know. Does anybody have any question up to now? Okay. So yes, we prove this one. Let's define another one actually. Okay, one more things we need to, let me write something, and then before that one, so let me write if we have here, what we have, I do have for the base case, I have only one number. But if my base cases is like a inequality, instead of n equal to 1, it was n between 1 to 2 to 3. If that was the case, we have something we need to make sure. Multiple, if you have multiple base cases, one of the most, if I have, let me write, multiple, oh my gosh, that's not good. If I have multiple base cases, so if I do have this one, let's consider the base. Base is not only one, it's gonna be P1, it's gonna show P2, and go all the way to Pn naught. So it means that what I'm gonna say, I say this is gonna be the lowest base case, and this is gonna be the highest base case. If I do have these ones, so I do have this one, I need to do the induction. How is the induction work? Induction should be for all n greater than n naught. Then we have P1 gonna hold all the way to Pn minus 1. And then we show it's gonna hold for Pn. So this is gonna be the way. So we show that it's gonna hold. So that's when you have multiple base cases, it's not only one. And then we have one question, exact same thing that we have. So let's go back here. I wanna add another question. Let's see, define another T of n for n in positive integer, then what's going to happen? N is between 1 and 2. If this is the case, this is gonna be 1. If n greater than 3, so let me remove that, we need a space. Okay, we say T of n is 1 if n is between 1 and 2, if n greater than 3, for T of n over 3 plus n. Okay. So, but you want to show for all n greater than 1, then T of n is less than n squared, or another way we can say that T of n is again is big O of n squared, because this is gonna hold. So, and then based on this one, this part, we still say this part is gonna be P of n. Actually, not whole part, this only this part. This is P of n. Okay. So does anybody have any suggestion how we should prove that? How we should prove that? So is anything there? So how we should go for it? Yes, now we have two base cases actually. We don't have only one, we have two. Let's go and write the proof. Okay, let's write the proof. Okay, now we have two base cases. Two base cases. One of them is n equal to 1 and n equal to 2. now because we have two base cases, we need to prove both of them. Let's just start with base cases. What should I say? For the base case T1, what do I have? T1 is equal to 1 is less than n squared. It means less than 1. So it's hold. So okay, this is hold. And let's do the second part. T of 2, which is gonna be 1 again. 1 is less than equal to 2 squared, which is gonna be 4. So this is gonna hold again. So you say, okay, base cases hold, so great. So now let's do the second step. What is the second step? We say, okay, now we go over here for all n greater than 2, because we already show 1 and 2. For all n equals, if I consider P1 is correct, and then consider this is correct, and then show that Pn is correct by induction. Okay, let's say, okay, let n greater than the, again greater than the 2, n greater than 2, assume, what do you assume? For all, again, we say for all k, because we say all of them is correct, k in the range of 1, k between 1 and n, then, and then we say for all in the range of this one, that what's going to hold? If that's the case, then we say, okay, tk is less than k squared. So, and then if we do have that one, what we should show, we just assume it, we must show that Tn is less than n squared. So that's what we need to show. So that's the way. So now let's start with this one. I say, okay, if I want to show this one, I say, okay, then T of n, what is T of n? For n greater than 2, or any greater than 2, or it's equal to 3, it's going to be the equation. It says for T, the lower of n over 3 plus n. So is it clear up to now? Does anybody have any question? Nobody has any question?
No.
Okay, great. So if that's the case, let's consider, okay, this is less than equal. Why? Because I say, I know for any k between 1 to n, it means it's not equal to n, anything. It's going to be tk less than k squared. So if that's the case, I keep the 4 is not, but I consider this one. It means if I consider this one, this part to be k, so then I know that tk is less than k squared. So what does that mean? It means that this is less than, this is gonna be less than n over 3 squared plus n. Again, you need to write here. What we need to write is that I consider this one. Well, how should I consider it? By the induction hypothesis. I consider this one an induction hypothesis for what? With k equal to n over 3. This is some of the things you need to write. Why? Because I need to consider this one too. What is that? Why n then n over 3 is between 1 and less than n, which is hold. Why? Because the minimum n that I have here in this equation is 3, because this equation holds for n equal to 3. If I consider 3, so 3 over 3 is become 1. The floor of 1 is going to be 1. So 1 is greater than 1 and less than n. So that's going to be hold. So this equation, this induction hold for this. When I assume, I need to assume something to be true. So that's the thing. So okay, this is going to be hold. Let's continue proving. So okay, if that's the case, if I do have this one, n over 3. So what else I know? I need to get rid of the, if you have ceiling or if you have floor, you need to use the equation about ceiling on a floor that I explained in the section, I think in the lecture first. Since, what do we have? We say since the floor of the any number is less than the number by itself. Let's use this one. If that's the case, it means it's less than 4. I need to do this one. I say, okay, n over 3 floor is less than n over 3 by itself. And then I do have this squared plus n. And then what's going to happen? So I'm going to have n squared over 9 plus n. So, and then let's do this one. I said, okay, this is going to be 4 over 9 n squared plus n. So what's going to happen here? This is going to be less than what? Anybody can tell me this is going? Yes, this is going to be less than n squared. But why? Because these numbers is less than 1 all the time. So n squared rate, when you consider n squared and n, the rate of growing n squared is greater than n. So we can consider this one drop. But this one is less than, because this number is less than 1. So this is going to be the whole. So if this is going to be the case, so that's going to be hold. But let's prove this one. Let's prove why it's gonna hold. It's not gonna say, okay, it's gonna hold, but let's prove it. Let's say, okay, first of all, I know n is greater than 2 because I know that I'm here and it's greater than 2. If n is greater than 2, what is gonna give me? It's gonna give me 9 over 5 is less than n. So let's consider this one. And then n less than 5 over 9 and a squared. Why I consider 9 over 5? Because I need to consider one of the ns squared to be outside. So if that's the case, if n greater than 2, n is greater than 9 over 5, which is gonna be more than that number. So that's gonna be the holding. So if I just put multiple n by both sides, so what's going to happen here, what I'm going to consider is like a 4 over 9 n squared plus n squared greater than n. So, no, I think this is going to be minus. This is going to be holds, and it's like a n plus 4 over 9 n squared less than n squared. Because this is going to be 9 minus 4 is going to be 5 over 9. So that's going to be hold. So that's the reason it's going to be hold here. So you start with this one, you consider n, and then, okay, if n is 2, so that's going to be hold, n greater than this number, which is going to be less than 2. So it's okay, this is going to be hold. I just consider this one, and this is going to be hold. So now I do show this is working. So by induction, so here, that's what I'm going to write. It's again, it's proved. Proved by induction. And what I'm gonna say is like a t of n is less than n squared. And then we show that this case of that base case, we show base case for different, actually 2 different base cases. Does it make sense?
Yeah.
Anybody has any other question? Okay, I think We are clear here, so there are different ways that you can prove this one. There's so many things. There's so many examples that's like you can try. So you're gonna see lots of like this kind of question in the final homework or just quiz in future. So that was the first case. Let's go back and I'm gonna talk about graph theory actually. Okay, let's see. I want to do short introduction to graph. So let's go down. And then let's do a short introduction. To graph. Does anybody know anything about the graph? So you know about graph, am I right? Yeah, directed graph, undirected graph. Yes, overall talking about graph. You probably have some idea what is a graph. Just want to remind you guys, because I want to solve an induction proof on graphs, I need to explain a little about graphs. So we say a graph, G is a pair of sets, which is gonna be shows by V and E. So G is a pair of sets. G is equal to V and E. First of all, we should say V shouldn't be equal to empty, are called, the first one is gonna call the vertices. Probably this is gonna be a little better if I make this. Okay, these vertices, and then the element E are called edges. So this is gonna be C definition. We consider that the vertex is not gonna be empty, and so the edges is the element which is gonna be called edges. But how we should show that one? So each edge, okay. So we can consider each edge joins two distinct vertices, which is gonna be called its end, because it's considered between two join. It's going to join two distinct vertices, so it's going to be end. So no two edges have the same end because it's not possible. So we can say edges is the unordered pair of vertices, two elements subset of vertices, two elements of that. So how can I show? Because if it's two elements, so I can say E is the subset of vertices by two. Because why? Because it's gonna be two elements sets of two. So if I want to show this one, it's okay, this is gonna be two element sets of V. So this is gonna be how it's gonna show. For example, this is gonna be this one, this is X and this is Y. It means I have two vertices, distinct they should be distinct. And this is gonna be this consider. This is gonna be edges. So it's gonna be X and Y. And I can consider this way, I can write this way. Any because it's not directed, so any of them is correct. You can say X and Y, you say XY and YX. They're all shows that this is the edges between two vertices. So let's have an example. So let's see one of the example I want to show. Let's see, example. So I do have this one, for example. I do have vertex 1, 2, 3, 4, 5, and 6. Let's just consider connecting these two. This is gonna be edge 1, 2. I write it like this because it's connected 1, 2 or 2, 1. This is another, this one, and then you can see 3 to 4 or 2 to 5. It doesn't matter actually. So like I just connect them. So if I want to say, let's talk about everything. So here, this is gonna be, if I want to consider the degree, let's talk about degree of 6. It means degree of these vertices. How do you consider degree of these vertices? What do you consider for degree? Actually, degree shows the number of edges connected to that vertices. So it's 1, 2, 3. So degree of these vertices is going to be the number of edges is connected, which is going to be 3. And then if I want to show this one, this between this edge is edge 2, 5. It's connect vertices 2 to 5. So let's write this one. So I want to write it. So, okay, V is going to be how many vertices do I have? 1, 2, 3, 4, 5, 6. This is my vertices. And then if I want to consider my edges, I need to show them. So I do have a connection between 1 and 2. I write 1 and 2. I have 1 and 3. I have 2 and 3, 2 and 4, 3 and 4, 2 and 5, 2 and 6, 2, 4, 4, 5, 4, 6, 5, 6. I think I wrote all of them probably. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Am I right? Did I write everything? 2, 3, 2, 4, 3, 4, 2, 5, 2, 6. I think I wrote 2, 5. This one 2 times. Okay, so now it's correct. Okay. Is it clear?
Yes.
Okay. Some of the concept we need to know. When I say we says 2 things. 2 is, okay, let me write it down. So 2 is adjacent to which one? For example, 2 is adjacent to 3, 4, and 5. Let's say it's adjacent to 5. Because it's the neighbor of 2 is like 5. And houses, for example, we say 2, 5 joins 2 to 5. That's the other things that we use. So some of the concept you need to know: adjacent, joins, and then let's see what else we need to know. So we need to know 2, 5 has ends 2 and 5. So what is the other one? It's the definition of ends. It means it ends connect these two together. And then what else? So let's talk about another adjacent. So we can consider 2 edges can be adjacent. So for example, 1, 2 and 2, 5 are adjacent to. I can say, okay, 1, 2 is adjacent to 2, 5. Or what I can do, I can say 2 is yes, that's it. I think that's what we need to know. Okay, that's the first thing we need. Does anybody have any question on this? Probably, yeah. Okay, so it's clear. Let's see. We consider this one. We already considered some of the concept, not all of them. There are more about that one. Some of the notes that you need to know. Let's add a note here. Note. For graph, this is not allowed. It's not allowed. So first, if this is not X and this is Y, this is not allowed. And then we don't have this one. We don't have this one too. Yeah, I think that's it. So we have this one. Let's see. What we are trying to say, we want to define a few other things here. We talk about like, what is the definition of the vertices? What is the definition of adjacent? And then what we are going to talk about, like we talk about like, we can talk about cycles and the other things too, are connected or disconnected. So one of the things I want to explain, like we say, what is a tree, or let's write about that one. So I'll say like, let X and Y be vertices. And what we say X to Y, it's a passing G. Passing G is a sequence. So what does that mean? It means it just start with X and then go to some sequence in the like vertices. They start with V0, go to V1, then V2, and go all the way to VK and then reach to Y. So this is the sequence of vertices in which, so it's okay, all VI and VI plus 1 is gonna be in definition of edges. It means I do know that this vertex is coming from the definition of vertices, but any vertices like 0 and 1 is connected, is in the edges. There is an edge between 0 and 1, there is an edge between 1 and 2, there is an edge. This is gonna be like the whole path moving from one to another. For what? For all I from 0 up to K minus 1. Why? Because we say all the way to K, it means that K minus 1 is going to be connected to K. So that's it. We do have this one. Also, there are no repeated vertices. It means that you are not going to have 0, 1, 1, 0. We don't have it. It's just going to be except two things that going to be happen, except they're not repeated, except if it goes a start from one point and get back to the starting point. Possibly if when X is equal to Y. It means you start from the start point and go back all the way to the where you start. If X is equal to Y, then we say path is closed. Does it make sense? It means you start from the beginning, go all the way to the path at the end. So it's like the path is closed already. Okay, so let's write a trivial path, one of the really trivial paths. It's going to be path of X, V0, Y. It means there is only one vertices. Start from X, go to Y. That's it. A non-trivial closed path, for example, is going to be like something like this. It's a start X. This is going to be V0. And then it's go to this one, connect to this one, and then all the way to this one and get back to here. It means this is the path. Start here, go, and all the way go. This is the closed path. This is non-trivial. And then if it's going to be like this, start from X, go back to the X, it's called the cycle. It's called the cycle. So we already have the cycle. So, and then let's see, if we have a cycle, we have another thing. So, and then we have another length of path. What is the length of path? Is equal to number of edges traversed. It means when you walk through all the edges from one point to another from the path, for example, here, this is trivial. The length is 1 because I start from X, go to Y. So it's only one edge. So it's going to be 1. And if you have more, it's going to be, I don't know, 5, 6, or anything. So let's see, for example, some cycles. So show some cycles. Like this is a cycle. This is 1, 2, 3. So you can see I start from 1, 1, 2, and go back to 3. What is the length of this one? Anybody?
Three.
Yes, exactly. The number is 3. Let's go back and try another one. This is cycle because this is gonna start. Let's see. Let's see, this put 1, 4, and this is 3. Oh. This is gonna be 4. What is gonna be length of this one? Anybody?
4.
Yes, exactly. So it's gonna be 4. This is gonna be 4. So we have more concept. We talk about if this is graph is connected or not, or what is subgraph, and I'm gonna talk about these ones too, about like graphs, and then if there is a direct graph or is not. Let me talk about connected graph, and then we are gonna have our quiz. So the next concept I'm gonna talk about, we say G is called connected if for all X and Y in V, G contains it contains an X to Y path. So it means all of the edges, all of the vertices is connected to each other. So it means that, for example, this definition, let's see. If this is 2 and this is 5 and this is 6, this is not connected because for any, like for example, from 1 to 6, you don't see any edges. So this is not connected, or this one. All of this, 7, 3 to 7, and then to 8. As you can see, this one and this one, this connection between 2 and 3 is not connected, or 4 and 9. You can see all of these ones are not connected to each other. So there is a separation between 2 and 3 and 4. So they're all separated. This is part 1, this is the other one, and this is the last one. So this G is the overall. The overall G is started from 1 to 9, but you can see there is not connected. So it says this graph is not connected. So it means this graph is not connected. So that's one of the other definitions. So that we say, okay, this graph is not connected because you don't see, based on the definition, for any X and Y in V. So we have So vertices start from 1 to 9. So we should have any connection between 1 to 9. G connects any x, y. X contains any x and y path. It means that I start from 1, 2, and then go to 3, 4, 5, 6, and then we don't see that one. That's not, it means that it's not connected. Is it clear? Okay. Okay, if it's clear, let me post the quiz already. So, and then you have like, I give you guys, I think 20 minutes. I think 20 minutes is a lot. So probably you guys gonna finish by 10. So just give a margin for that. So let's see. Let me see the preview myself and then. Let me fix something here. So and then. Okay, so let's see if you guys can see it. Can you see it?
Yeah, it's up.
So I think you can access it in 1 minute because it's gonna start at 6 and then it's gonna finish at 6:20. Yes, and then so let's see. Let's just wait for 1 minute. So and let's see if you can guys start it. So I just give access to upload because it's hard to type here, and I just asked yesterday, so you can write handwriting or LaTeX, Word, anything that you like. So okay, you guys can start. It's quiz 3. It's a small, lowercase everything.
What?
Actually,
What's the? Oh, question. Sorry.
quiz 3 lowercase. Let me know if you have access. Do you guys have access? Okay, great. So I just mute and you guys can upload the quiz.
I'm sorry, Professor. What's the quiz code?
Quiz 3, lowercase.
Oh, it was uppercase.
Lower. Everything is lowercase.
Okay, thank you.
You're welcome. Yeah, if you type it somewhere and you want to take a photo and just upload it, that's fine. Yeah, as long as that's your work, yeah, it's okay. You can just upload it. Okay, we do have, I think, 7 minutes. I think probably you guys need to finish by now because we knew the homework stuff. But let's see, we'll wait a little more and then I will start teaching the other part. Yes, yeah, that's true. About LN. Mhm. LN is the natural log, so. Okay. Let's try to make sure you wrap it up the quiz, so and then I can start get back to what we finished. Okay, stop. Go. Okay. Five more minutes, so it's try to make sure submit it before it close. Okay, I think probably it's enough. So I have 3 minutes. I want to get back to the teaching the other part. So
Yes, sir. It's not letting me upload it. Can I send it like as an email?
why it doesn't? You know
It's
why?
It's not letting me access the quiz on my laptop.
Interesting.
To
You can
upload.
access Canvas. Or
I can access Canvas, but I cannot access the quiz. It just shows loading, loading, loading.
it's okay. Send it through email.
Okay, thank you.
But please send it right now so it doesn't miss that time. You know. Does it make sense? Send it through email right now. So because of the time.
Yeah, I'm sending you right now.
Okay, great. So let's start getting back to what we are talking about. So we have a subgraph of G is a graph. We said we are talking about subgraph of G. We say subgraph of G is a graph H such that two things hold. First, the vertices of H is subset of the vertices of G. This is going to be the graph G. And also the edges of H is going to be subset of the edges of G. That's subgraph. So it means that we have subgraph of this. Let's see, for example, what is a subgraph? Let's see. If we consider that we have, so we can note, for example, this is going to be subgraph 1, 2, 5 from all the graphs, and this is subgraph. What does that mean? Let's see. This is the V and E, V of H and E of H. It means that we just consider, instead of whole of these, I just consider vertex 1, 2, 5. So I get the vertices is going to be 1, 2, 5, and this is the edges. I just consider this one. This is going to be this V, H, and E, H. So it's going to be this one. So let's see. If I want to consider this subgraph, I just have 1, 2, and okay, let's go and just write it in the next page. So let's write this one. I have 1, 2, and 5, and then I say 1 connect to 2, 1 connect to 5, 2 connect to 5. This is going to be consideration. Because this is all the edges are connected, so second, this is the connected subgraph of G. This is coming from G. As you can see, G is here, but we just consider 1 to 5. This is going to be subgraph of the G. But let's consider another subgraph. Let's consider 2, 3, 6, 7. And the edge is going to be 2, 6, 3, 7. Let's go above. I have 2, 3, 6, 7, 6 and 7. Let's consider this one. So it's 2 and 6, 3 and 7, 2 connected to 6, 3 connected to 7. This is another subgraph. Let me write it better so I have a space. So this is gonna be 2, 6, 3, and 7. This is a disconnected subgraph of G. So this is subgraph, but this is gonna be disconnected subgraph of G. So that's what we, yeah, that's the reason I mentioned. I give you guys 20 minutes because the 5 last minutes is just for uploading. Yeah, send it through email, but don't do it, please, because it's gonna make my life hard, because not only I need to grade the quiz through Canvas, I need to grade the quiz through my email too. Please send it through the email, but from the next time, make sure that you upload it to, that's the reason I start teaching in 18. It means that you already need to upload everything, but that's fine. Send it through email, but not the, this is the last time. So because it makes life hard for grading. So, okay, let's get back to subgraph and then connect about a few things. It's okay. I want to talk about a subgraph H of the subgraph of H, G of G, subgraph H of G is a connected component if and only if this is gonna hold. First, H is connected And second, H is maximal with respect to 1. What does that mean? It means that if it's connected, it's going to have all the edges that's going to consider with 1. It's going to be maximal with respect to 1. So this is another definition of component. Let's go and talk about another definition. We need all of this definition later because we need to prove induction. We need to know what does that mean. Let's go to G. Is called cyclic if and only if what? It contains no cycle. If there is no cycle, we also call it a forest. So let's see. For example, I do have this graph. Or this one. So this is 3 different graphs, but none of these graphs have a cycle. It means that if I consider X here, it's not going to go and get back to it. So this is 3 different graphs. What I can write here, I can explain all of this graph in this table. So there are 3 of them. Let's see the number of the vertices and the number of the edges for each of them. Actually, I need 1. Let's see. Probably I can do better. Okay. So how about the number of, for the first one, how many vertices do we have? Yes, we have 6. And how many edges do we have? Okay, correct, 5. How about the other one? How about now 6 again? How many edges do we have? Okay, exactly, 6 and 5. How about the last one? Exactly, we have 5 and 4. So this is gonna be the definition, and then we have different how many edges and how many. But let's go back to last definition here. A graph is a tree if and only if it is both connected and there is no cycle. So this is going to be definition of tree. We talk about what is tree. So okay, there is no, it's connected, but there is no cycle there. So we explain all of these things about graph. Now we want to solve one of the induction problem. That's one of the reasons I explain everything in the middle of the induction. So let's go back and talk about one example. What is the example? We say prove for any n greater than 1 if T is a tree on n vertices, it means has n vertices, then T has n minus edges. What does that mean? We say, okay, I do have a tree and then it has n vertices, and then I will show that it has n minus 1 edges. That's the thing that I'm gonna prove. but we need to prove it by induction. I want to prove it. So how do you prove it? So let's write it in a better way. First of all, before writing the proof, let's write it in a mathematic way. So it's okay. We say for any n greater than equal to 1, based on the definition here we have, n greater than 1, what does that mean? It means that if I consider the number of the vertices for this as a vertices of t is equal to n, it means it's gonna give me, what is gonna give me? It's gonna give me the number of edges for that tree is equal to n minus 1. So that's the definition that I do have. And this part, still you can see, I switch the tree to the definition based off the number n. So this is gonna give me p of n. So now I can prove it with induction, because I already switched the definition of graph and tree to one problem with induction, so I can solve it. Is it clear now? Does it make sense? Okay, let's prove it. Okay, let's go to the proof and see how we can prove it. But I want to do induction. What is the first step of induction?
Base.
Yes, what is the base? Let's go to the base. Let's see. Base is 1, as you can see, n is equal to 1. Let's t be a tree with 1 vertices only. Based on definition, we say the number of vertices is equal to 1. The number of edges is going to be 0. So that's going to hold, because the tree does have only one. The 1 point is a tree too, because it's connected and it doesn't have cycle, because there's nothing that makes it disconnected. So it's going to be a tree of only 1 vertex and no edges. This is hold. Okay, we say, okay, this is hold. In this case, what do we have? T has 1 minus 1 is equal to 0 edges. That's work, so, which is correct. So we already know this is correct. So let's see, and based on this one, let's do the induction. The second part, what we are gonna say, also, okay, for any n greater than 1, let's consider this one. I know P1 is gonna be true, and then let's see. If it's correct to Pn minus 1, then what I can show this is gonna show Pn is true too. So let's see how we can prove it. It's okay, let n greater than 1 be arbitrary. So let's consider this one. What we are gonna assume, again, we assume for all k in the range of k greater than 1, less than n, because it's not going to consider n, that what do we have? We are just going to consider if t is a tree on k vertices, then t has k minus 1 edges. That's the definition, assumption. So, okay, if it's equal to k, it means the number of edges is equal to k minus 1. That one we assume this is true. What we must show that if t is a tree on n vertices, then t has n minus 1 edges. So that's the thing. We consider, okay, if it's hold for k, now it's gonna hold for this one. Okay, let's prove it. How we should do that? Okay, I say, okay, let's see, I want to say let's T be a tree on n vertices. I know this is gonna hold. I need to show the number of vertices. Okay, I say, okay, pick any edges. Because I know it's a tree, I pick any edge. If I consider this one, E, which is gonna be in the edges of that tree, and remove it. Okay, let's do something. I just consider one. Let's, for example, if I do have a tree, let's consider I'm just gonna remove one of them, for example. That's one of what I'm gonna do. So what's gonna, if you remove one of them, you already know the tree is a connected graph. If I remove one of the edges, for sure, this is gonna be disconnected. This connected T into two subtree. Let's call them T1 and T2. Why? Because there is no cycle, and if you just remove one of them, it's gonna be two different subtrees, which they don't have cycle either. So what's going to happen? If I have two now, let's say the number of the vertices for T1, the first tree is K1, and the number of vertices for the second tree is K2. And what we are going to say, we are saying for sure K1, because we just disconnected K1 from 1 to n is less than, and because now we lose one of the edges at least, or K2 is going to be equal to 1 and less than n again. So if this is the true, I just assume if I have a K here, if I have K between 1 and n, and then the tree has K vertices, then tree has K minus 1 edges. So that's whole. So by the induction, so hypothesis, what we have, we can say, okay, the number of edges for T1 is gonna be K minus 1, K1 minus 1, and then for the edges for second tree, subtree, is gonna be K2 minus 1. And we note that, we note that because we just separate the vertices, K2 plus K1 is gonna be n, because we just remove one of them. Since that's the case, since no because we didn't remove anything, we just split them, we remove edges, we didn't remove vertices, so this is gonna be whole. And then what we are gonna have, so if that's the case, therefore what we are gonna have, therefore, if we consider the number of edges for the first tree, it's gonna be the number of edges for the second tree and first tree. So it means that this two plus 1. Why that's the case? Because I explain here, I just consider removing one of them. I just pick any edges and remove it. And then if I remove it, it's become two different subtrees. So the number of edges for the first tree is gonna be two of them based on the one I removed. I removed one of the edges already. So if I consider this one, I know based on the hypothesis, the number of edges for tree 1 is going to be K minus 1, K1 minus 1, and the second one is K2 minus 1, and this is going to be plus 1 for the one that I've removed. It's going to be K1 plus K2 minus 1. And then I know already this is n, this is going to be n minus 1. So we proved it already. So we just proved that this is going to be whole. So we just started that was my Pn. I show, okay, consider this one. I show the base case. And then after base case, I show it's considered for any P1 to Pn minus 1, which is considered K. So if that's it, that's hold. And then I'm going to show that it's going to hold for the whole Pn. So I just did this calculation. I show I already have 2 subtrees and I remove one of the edges. So this ET, the edges of that tree is going to be the edges of that 2 subtrees plus 1. I just put it on and show it. So it's based on hypothesis is already shown. It's already shown that it's working. Does it make sense? Okay, sounds good. Okay, so we show induction. So I'm gonna teach another things about induction principle tomorrow. So yeah, I think we are finishing this today. Let me save it and just upload it there too. Okay, so probably we are good to go. So if you don't have any question, have a great evening. Talk to you guys tomorrow. If you have any question, you're gonna stay in the call and ask.